computer. Okay, it is still sharing. Okay.
Okay.
Um, check if it is still sharing. It's sharing. Okay, so one of the reason uh before you start saying anything or deriving Schrodinger equation, I would like to say one specific interesting characteristic of Schrodinger equation is that uh this equation, Schrodinger equation, is something like Newton gravitational law. Basically, when I say it is analogous to Newton gravitational law, that means the Newton gravitational law that we are familiar with, F proportional to m1 m2 divided by r square, it came to Newton without any prior equation. That means that is the first equation, or that is the beginning of Newton gravitational law equation. Before that, there is no equation. Usually, the way science works, actually, there is something. From there, people start working on it and they develop it, and that develop make the further development actually. It happened to the Newton's gravitational law. It also happened to the Schrodinger equations. We know the solution, that this is the solution, but we don't know from where it came from actually. So it is surprising. And one of the reason actually we can analyze the characteristic of Schrodinger equation because it is the second degree wave equation actually. If you guys in high school, you know there is an equation for the wave that is, uh, let's say for a pendulum, what will be its position at time t and the position x. The formula for that is equal to x equal to a sine omega t. Basically, that is the formula. So let me yeah, I'm looking for an annotation or also pole. Sure, then whiteboard. Okay, there is a whiteboard. Let me share it. I believe it will be helpful. So basically, we know x equal to a sine omega t. We are very much familiar with this formula. This is the wave equation formula because at t, we know when the amplitude will happen for 90 degree. When this whole value is pi by 2, that is 90 degree, then we will know it will be x will be a. But this is a solution. The solution of the equation is d square over dt square plus uh, there are some constant equal to 0, something like that. So basically, this is the second order or second degree differential equations actually.
Okay.
So if you start working with any waveform actually, that will be the very beginning. It should be always second degree. And one of the important question is why it should be always second degree actually. And reason is that actually, uh, if we do integration, let's say sine x, if we do integration of sine x, so what do we get? I think it's better to do cos x because there will be some positive, just for making our life easy. Okay, this is cos x. So that means uh, integration of cos x actually sin x, but we are getting a plus c, a constant, if you do integration right now. Let's do one more time integration over this. Integration of sine x, we will end with minus cos x. I believe I'm right. It should be minus cos x. Then you are doing integration over it. This is c1. Then you are getting c1x. Then you should get another constant, c2. That means if there is a differential equations, that is 2 degree d square x over dt square, that is 2 degree. That means you have to integrate twice. That means you will end with two unknown or two constant. Basically, these two unknown is your x. That's the thing you don't know. Basically, where is it at a particular point and particular time? And another thing is your time is your unknown variable actually. So that's the very basic thing actually. So that's why any wave equation it should be second order differential equations. That means there will be degree 2. So basically that was the only thing Schrodinger knew. And from beginning, having that thing in the mind, Schrodinger then wrote the Schrodinger equation. And from there, we start our calculation. We know how to solve a second order differential equations. From there, we find the expression for the basically wave function. Basically, Schrodinger wrote the second order differential equation for a wave function. And if we solve it, we got the solution for the wave function. And for that wave function, the quantum mechanics begin. So for any question,
No, I'm good.
okay, good. Okay, let's go to the book. Okay, so on the very first para, they start basically they were explaining this figure actually. Uh, this is there is a force, there is a velocity. Force is a function of x and t, and as it is moving, so time changing, as time evolving, the position is also changing actually. But one of the line I'd like to focus on actually, we know that force has a relation with potential actually. Basically, that is the uh, gradient. Gradient means first order differentiations, first derivative with v. V is the potential actually. So
Mm,
if to get a force, we need a potential. We do the first derivative and we put a negative sign actually. It also happens for almost everything. It doesn't matter whatever the potential is. This potential could be electric potential. If you do the first derivative on an electric potential, you will get an electric field. That is also a force. Electric field also a force actually. If your potential V is potential for gravitation, let's say mgh, there is a rock, it is placing it on a h distance from the ground, then the potential will be mgh. Now if you do the first derivative, you will end with f equal to mg. So that means it doesn't matter whatever the potential it is. If you do the first derivative, then put a negative sign, then you will get a uh, force. Okay. So, okay. Okay. And if we just write f equal to ma, a means second derivative of x because dx over dt, d square x over dt square, and you just do the same thing. So do you see there is a second order differential equation, the way like I just wrote or explaining the wave equations? That means if you solve, that means you do the double integration, you will end with a solution actually. That means you will end with a solution that will say at particular time x and particular time uh basically at particular time t, what is the position, how much distance this object or particle covered actually.
Okay.
So any question? You guys can also make questions in Bangla if it is fun, but I was just trying to make sure that so other people, in our Discord community, there is also community from India actually. So I wanted to make it recording so that they can also, yeah, listen to it actually. Okay,
Yeah.
but yeah, go ahead. Any question?
So far so good for me.
Okay, okay, good. Mm, and yes, and these so on the first paragraph, the discussion was about classical mechanics, and here this discussion is the quantum mechanics. Like I was saying, they were looking for the similar kind of expressions, the
Hmm.
second order differential equations. Let's do some comparison actually. We are seeing the same kind of behavior, that there is a second order, there is a first order, and there is something constant actually. Let's don't be bothered about it. So, okay. So this is the famous Schrodinger equations actually. So, uh, okay, just that is the expression for now. We will get more into the characteristics of it. But only thing is there is an imaginary IH cut D psi over dt. So the confusion or the question that may came, so basically that right hand side, do you see any imaginary component? All the thing on the right hand side you see they are real. You
Hmm.
know, in mathematics, most of the cases people love to deal with complex number actually. One of the reason it makes things easier. Question is how? If there is a complex number, we can just write it into a polar form. I think in high school, in the polar form, that means there should be an amplitude that is R. Every complex number, there is an amplitude or R, and there is also an argument that is theta. So that means if there is a complex number, you just can write it into R and theta actually. So that makes life easier. So on the Schrodinger equation, on the right side, you only see the real component actually. There is no complex component. But on the left side, you only see the imaginary component actually. The analogy is actually why then basically that is one of the most surprising and interesting thing that Schrodinger equation, right side, one side it has a real, and another side on the left side it has a imaginary actually, but still we have the solutions actually. And how does it make sense actually, what is going on in here? So it will take some to get adjust with it, but for now we'll say let's believe it.
Yeah.
Because one part I convinced you that the Schrodinger equation, even though this is the beginning, people or Schrodinger came with these equations actually, but it did not came from like heaven, from heaven, uh, that one day maybe he was dreaming, uh, and he came into with this equation. It didn't happen that way actually. Basically, it is a wave function And wave equation have a specific property that I was explaining a little bit earlier, because it is a second order, and these equations shows all the characteristics. But only question is right now, keep it in mind that left side imaginary, right side is real actually. And other thing is quite just if you guys go through it, it will be easy to read. So okay, now one of the very important questions actually, what is the significance is two statistical interpretations. The equation that you see in 1.3 actually, that is the Bond statistical interpretation or Bond rule actually. What does it say? One of the very famous thing or quirky thing that you know about quantum, uh, especially in the science fictions, there are sci-fi writer or sci-fi communicator or popular science communicator who says that the wave, it is okay to understand that an wave has a waveform, and Max Planck, who first introduced that wave propagates, the wave propagates as a unit. It has a photon. The unit is called photon, and he somehow tried to coin the term quanta. From there, the quantum came actually. Basically, that quanta is a particle. It shows the particle property. That means wave has a wave property, also the particle property. But also, if you go through the history, how the light, what is the property of the light, you'll find that Newton is a big proponent of particle property, because he assumed light is a particle actually. Basically, each particle, light color particle has different property. Blue color light has different particle property. That's why we all see the different colors actually. Then Huygens basically came with the theory that no, light is a wave. And after that, the Young shows his famous experiment, that is a double slit experiment, and it definitely showed that light is a wave actually. There is no other options actually. Uh, you can explain such a unusual property by Young double slit experiment other than wave. That means light is wave, and it was established around 1800 actually. And one of the thing then, from there, the Maxwell basically developed the theory for his famous Maxwell equations, and he is the first person who uh, by mathematics calculated the velocity of light using the wave equation property actually. So that's a little bit history about the wave. Then when the early 1900 actually, when people started working on vacuum chamber, they find the particles. They started finding particles. Basically, that was the time when the radioactivity related research was on full blown. Second order, first order is happening. So people need some kind of destructive weapons actually, and the government invested a lot actually during that time. All the particle physicists or physics, atom related activities or research uh, it developed. And that time people find that electron also shows a wave property, like the early 1700, the way Young showed that light is a wave because it shows interference property. Particle, it can never show this kind of interference property actually. Basically, it came from the Young double slit experiment. The similar thing, it is found in lab in early 1900th century, um, for particle of electrons actually. They found that it doesn't matter what the particle is. It could be electron, it could be proton, but you'll find the similar double slit property actually. Basically, on the book, there is a figure, this figure. Let's talk about a bit about this figure actually. So this basically for the light, you will see the figure D. You will see some fringes. This is the uh, yeah, for the light, you'll see this kind of band actually. You'll find that, okay, this is maximum value, there is minimum value, this is maximum value, minimum value. But for the electron, you are getting the similar kind of property actually. My question is, let's say if this is for electron, what could happen if it is for proton actually? Do you guys have any guess actually? Uh, Rather than electron, if I try to do the same double slit experiment, what might happen for the proton? Uh,
It,
before, yeah, go ahead.
I mean, I don't know. Probably the basic characteristics of electron and proton will come into play, and I'm not sure, but that's
Uh,
what like.
yeah, that's a good guess. That's a good guess. When we say basic characteristics, uh, what are the basic properties or characteristics you are trying to refer?
Like electron has negative energy and proton has positive.
That's cool. Okay.
That might affect the light waves.
Okay.
So it would have like what we're seeing in the electron image, it would be totally opposite for proton. And I'm guessing that it would be more scattered or something like that, or full of spaces or something like that would happen.
Okay. Okay, that's a good case. I think there is Tanbir. Uh, do you want to add anything? Go ahead. I'm hearing you. Hello, Tanbir.
Can you listen to me?
Yes, but you are very low. Can you be a bit, okay, I think it is very midnight. I'm sorry, but okay, can you make sure that you are quite hearable
Maybe
because you are very low. Yeah.
Muhammad Bhaiya is right. মানে ঠিকই বলছে আমার তাই মনে হয়।
Oh, okay. Okay. So you are quite agree with you, Muhammad. That's the way you go with by yourself?
You can call me Dipto.
Dipto. Okay. Dipto. Okay. Sorry, we should have the first introduction, but as yeah, I'm sorry, I was around 15 minutes late
That's
actually.
fine. That's
So, but yeah, end of the meeting, we'll have a little discussion about ourselves actually. Then we'll get the introduction, who we are and from where we are. Okay,
fine.
but let's finish the basic part actually, the main part. Okay, so Deepta was saying that okay, the basic characteristics will come into the role, and basic characteristics means the charge. Basically, electron has positive, sorry, negative charge. Proton has what the positive charge actually. There is also another important property actually. Basically, that is the mass. So basically, electron is lighter compared to proton. Proton is heavier. The mass of proton is very high actually. Uh, if you do further study, you will find that charge will not come into the play. Charge will not come into the role. Basically, the mass will be the role. Question is why the mass will be the role. One of the important thing, very interesting thing I can share you that even let's say for example, anyhow, we three persons, let's say for example me, you developed a device that for me or for human being, any human being in the world, you want to do the double slit experiments, you will find the same kind of property actually, same kind of interference, the double slit property that Young did for the light actually. But the difference will be for the I mean the main difference that will make the difference, it is the mass actually. Let me explain. We are a particle. For example, just for the sake of argument, we can say that we are particles. We also have wave, but our wave property is very small. It's almost negligible. That means if we have also wave that is very negligible, that is not very much strong, then the fringes or the maximum minimum band that will go, it will be very diminishing. That means it will be very weak. This property will be very weak. That means rather than getting strong band, strong thickness of maximum or a strong thickness of minimum for the light or for the electron, for us, if we can make double slit experiment, it won't be very strong actually, because our wave property is very much weak. Same analogy or same explanation goes for the proton. If we get this kind of figure for figure D for electron, for the proton, it will not be as strong, or as you can see, there is maximum, there is some dark spot. This is the very maximum spot actually, brightest spot. They are dark spot actually. You can totally distinguish, make a difference between dark spot or brightest spot for electron actually. But for proton, it will be quite difficult because proton has a mass, and that mass, as it is a higher mass, that means it shows higher particle property or more strong particle property rather than the wave property actually. So that means for the wave, uh, for the proton wave, this figure will not be as strong as electron. Does it make sense?
Yes. Yes.
So yeah, that's the thing actually. You will figure, I mean, so we, from this discussion, we ended with a very important characteristics that, or we ended with a very important or interesting things actually. Everything all over the universe, there is two property. One is the wave, one is particle actually.
Mhm.
Question is, does both property exist at the same time? Uh, Basically, that's where Einstein was a totally, basically Einstein was against quantum mechanics actually. And if you guys read the history of quantum mechanics, you will find that Einstein was really against quantum mechanics because he felt that this should not happen actually. The reason actually, I made a questions actually, I did not answer it. The question is actually, does wave and particle both property exist at the same time actually? First of all, it exists at the same time. That was the proposal actually. It exists at the same time actually. It exists at the same time. Uh, Basically, Niels Bohr was a big proponent of this kind of idea actually. As Einstein was against this kind of idea, uh, but Bohr was with this idea. So they had a huge debate actually. They had a huge debate and they continuously fight it from 1910 to 1930. Those 2 years, they really fight it. They did a lot of seminars, symposiums after symposiums. Einstein tried to people convince that quantum mechanics theory is incomplete. We need something to make this theory complete. But Bohr said, no, you are wrong. That was the first time actually Einstein, I mean history, on the only time in the history Einstein was quite wrong actually about that. Okay, he was on the wrong side of science.
Wow.
That was the only time. So, but Niels Bohr, he was very young. Einstein was on the peak time of his famous relativity things. So he did his best to totally destroy Niels Bohr actually. But luckily Niels Bohr got some famous person with him actually, like Schrodinger, Max Born, Wigner, all those people were with Niels Bohr actually. So let's try to understand why Einstein was against these things actually. Try to understand the Einstein um, uh, understanding that actually uh, why he thought that the theory is incomplete. Let's say, for example, the idea of the Bohr was trying to say actually. Uh, for example, let's say there is a moonlight, as you are on the night part, moonlight in Bangladesh, on the sky of Bangladesh. So there is a moonlight. So if, so that means there is a moon, full moon on the sky. You are just walking or wandering in the road. If you look at the moon, you will see the moon. But for say, you are not looking at the moon. If you don't look at the moon, does moon exist that time?
No.
I mean, one more time, the
Yeah, yeah,
question.
yeah. It does. It does. It
Maybe.
does. My bad.
Yes.
Okay, so that means, so there is a moon on the sky. You are looking at, you are seeing it. But if you don't look, it does not mean that moon does not exist at that time. So my question is, I mean, the idea is actually you are not seeing it, you are not observing it. It does not necessarily mean that it does not exist, right? It exists.
Yeah.
So that was the Bohr idea actually. That was the Bohr argument. Bohr was trying to say it doesn't matter if you look at it or you don't look at it. If there is a full moon, moonlight, if moon in the sky, moon is exist. Moon has existence. So that was the a Bohr idea actually. The thing that Einstein was bothered actually. Okay, I'm looking at it moon, so I can observe the beauty of moonlight when I look at it. But when I don't look at it, that means if moon exists at the same time, but I am not looking at it, so that means there is something missing in our equations. When I don't look at it, it says that moon does not exist. Do you understand the argument actually? Now understand, try to think about in mathematics perspective or physics perspective actually. On mathematics or on the science, we say we believe things when we can measure it or when we can observe it actually. So we are not looking at it moon. That means moon should not exist when you don't look at it, right? That's the argument. That means you are not saying it, you should not believe it. If you don't see something, you shouldn't believe it because you are not saying it actually. But moon exists. So that means that part is missing on our equations, right? It should exist when you do some calculation, do some solutions, whatever. It should bring your solution should show that even if you don't look at it, there should moon exist. But there is no such a property uh, that the observer or the person who doesn't look at moon, he will feel that moon does not exist, but moon exists. So that means there is this part is missing. You understand why Einstein said that the theory is incomplete? Because that part is not in the equations. That part is incomplete. So he put all his life effort after 1915 or 1920 to find that equations actually, find that thing actually. So, but does it make sense to you why Einstein was against it and why Bohr was with it?
Yeah.
Okay, so that is the very interesting thing actually. And then I think around 1965, Bell, John Bell, famously came with his Bell's inequality. And he said that there is a hidden variable. Hidden variable means it depends on the observer actually. Based on the observer, you can say the moon exists or moon does not exist. Let's say Tanbir and Dipto, you guys, one person is looking at the moon, another is not. So that is a contradictory, right? Let's say for Tanbir is looking at the moon, Dipto is not. Tanbir will see the moon, but Dipto will not because he is not looking at it. Bell was trying to say this is an inequality. If the observing moon, beauty of moon, it totally depends on the observer actually. So that means Tanbir is measuring the moon. That's why he can see the moon. But Dipto is not measuring the moon. So that's why he doesn't see the moon actually. So that's how he solved it. And later, around 1980s, Alan Aspect, he experimentally showed this property for photon. And later, I think 2023 or 2022, Alan Aspect won Nobel Prize for this experiment actually. That is a very recent development actually. uh, I think 2022 or 2023, Alan Aspect won Nobel Prize for developing experiment setup for barrel inequality actually. So he, on experiment level, he proved that, okay, yeah, Bell inequality is true. And then we came with the measurement property actually. We say when you measure something like Tanbir was looking at the moon. Basically, he is measuring the moonlight or he is observing the moonlight. That means he is destroying the quantum property actually. And that's how the wave function collapsing. That's how we will get the solution for the wave functions. That's how we can measure the qubit or particles or anything actually. So that means even if electron has a wave property, as soon as you measure it, it answers the particle property. But for Dipto, he is not measuring, he's not looking at the moon. That means he's not destroying. For him, the function will not collapse, it will exist. Do you understand? You guys two at the same time walking at the same moon, but for two different person, you guys have two different characteristics. That's how quantum mechanics is very, yeah, weird thing actually for a long time. But for now, it kind of makes sense.
Yeah.
Any question?
I was wondering for the like this is about the double slit experiment, right?
Oh, figure 1.4, yes.
So on that case, like how do I say it? Uh is there like any like what experiment did Bohr did, or like whoever like discovered this pattern? Like what experiment did they do to show the double slit experiment? I mean, like
For
that.
electron, I mean, one question, okay, if you're trying to say, okay, let's spend a couple of minutes to understand figure A, B, C.
Yeah.
Okay, panel A, B, C. On panel A, you see very small number of electron actually.
Mhm.
When you see very small number of electrons, actually, you cannot, you will not get the double slit experiment property actually, because even though it tries to accumulate accordingly, I mean, on panel A, the reason you are not getting like panel D, because the number of electrons is very small. This is kind
Mhm.
of particle property. You are increasing the number of electrons, then it start to making a form. There is a more, then you start making a form, but you still don't very visible. But when there is a lot of, then it shows this kind of property actually. So it takes some time to evolve, because there is in the wave function there is x and t. So it takes time, some time, um, to get this kind of uh, young double slit experiment property. But for the, if there is not enough number of electrons, you may not see young double slit experiment property, like the wave property. We can call it wave property. Figure D is the wave property. So when A, B, C number of electrons are low, you are getting the particle property. When there is uh, a good number of, or threshold number of electrons, then you are getting wave property actually. That is one thing. And you asked another part of the questions actually, what was the experimental setup for this kind of
Yeah.
uh, figure actually.
Mhm.
Uh, how should I say? Basically, on experiment, I think for the photon, if you want to, people use laser light actually. You know, people use laser light. There is a laser. Uh, Lab laser, obviously, not the laser you guys sometimes play with, or we guys play with. So on the lab laser, they use laser light. How they make the slit? Basically, they call it aperture. Actually, basically they call it aperture. So they make an aperture on experiment. I mean, in the lab, and then there is a screen. But the screen is the opaque screen. Opaque means kind of transparent, but not very transparent, because you want to see this pattern, this bright, dark, this pattern. So if it is transparent, light will pass through the screen. So they make it opaque so that it just fall into the screen. So the pattern falls into the screen. That's the uh, but to me it seems like actually you're trying to ask me uh, what more, what is the more specific things. For now, maybe I cannot be very much accurate, but I can give you answer to the next week. How
Sure,
does it? Okay.
sure. That's okay. Yeah.
Okay, but did you get your a brief answer what
Yeah.
is going on? Okay. Okay, so okay, very last part actually. Okay, like I was saying that So that means there exists a wave and particle property at the same time. But when you measure it, when we guys will measure it, will end with either particle property or either wave property. It should not be same at the same time. It
Mhm.
means when you want to measure it, you should not get wave function could be particle or wave. There could exist both property at the same time, but when you measure it, you should not get the same thing. You should not get both. You should either get particle or you should either get wave. That means it should collapse. It should collapse into something, either wave or either particle.
Okay.
So that is the Born statistical interpretations actually. So equation 1.3, Born is trying to say that actually that is the probability of finding a particle actually. In our case, like I was saying, we have wave, but our wave property is very small. So probability of finding wave, I mean, basically this equation for finding particle, because when wave function collapse, it ends into a particle. So probability of finding particle is very high in our case. For light, finding probability of finding a particle will be low because most of the cases it is wave actually. To make it a particle, you should do something else actually. Uh, you should set up your your experimental apparatus that way actually. But yeah, that's the summary actually for equation 1.3 actually. Uh, any question?
No, I'm good.
Tanbir.
No, bhai.
Okay. Well, so for now, let's okay, how stop uh, recording, then we get introduce by ourselves.